So, good morning everyone. My name's Adam Murdoch, I'm the CTO at Gradleware, and today I'm going to talk about Beyond Gradle 2.0, or Beyond RC1 at least. So this is a pretty vague title, so there's two things I want to talk about today. One is I want to run through the Gradle roadmap for the next 6-12 months, give you some idea of what we're going to be working on. Hans did talk about this briefly yesterday. I just want to go into a little bit more detail and talk about some of the motivations. And then I want to get into one of those roadmap items, which is scalability and making Gradle fast. So that, of course, is the first roadmap item. So scalability and performance in general is probably one of the major pain points for using Gradle in the enterprise. So we have organizations building massive software stacks with Gradle. And to a large degree, they're successful with this, certainly compared to some of the alternatives they have. But we can do better. So incremental build, it helps. Parallel execution, it helps. Configure on demand, it helps. But these stacks are getting bigger and bigger, they're getting more complex, the automation is getting more ambitious, so we just need to go faster. On the other side of that equation is we have developers running Gradle many, many times a day. So I change some code, I try it out, I run some tests, I commit, I do that again, I do that again. And Gradle's involved in some or even all of those steps. So Gradle needs to be responsive. It needs to be fast. So it needs to not do unnecessary work. It needs to aggressively reuse stuff that it's already done. It needs to do as much in parallel as it possibly can. It needs to be watching for changes and reacting to changes and predicting what the developer wants to do and what they're going to need, and doing that in the background. And ultimately, we want to go distributed, of course. So I'll come back to scalability in a moment. So the next roadmap item is what we call multiple platforms. And platform here refers to the platform that your software runs on. So you might be building stuff that runs on the JVM, or stuff that runs on Android, or stuff that runs on the native C runtime, or stuff that runs on my custom embedded device, or my custom container, or some combination of all these things. And generally, Gradle's pretty good at this stuff. People are doing this stuff successfully now, particularly the JVM stuff, the native stuff, and the Android stuff. It's pretty solid. But what we're seeing is that some of the history of Gradle as a Java build system is kind of starting to cause us a bit of grief. So Java is actually pretty simple to build for. You take some source, you compile it, you build a jar, you're kind of done. You take that jar, you can compile other things against it. You take that jar, you put it somewhere, you can run it. You take that jar, you can run some tests against it. So everything that uses that software just needs the jar, and there's only one jar. And so there's this assumption in Gradle that isn't correct, is that every piece of software produces one artifact. I mean, there are ways you can tell Gradle that's not the case. There's still that assumption there deep in Gradle. And that assumption doesn't work. It doesn't even work in the JVM when you consider things like Java 5 versus Java 8. You consider Scala 2.10 versus 2.11. But in the native space, this just completely doesn't work at all. So in the native space, I need to build my binaries for each platform. I build Windows 32-bit, I build Windows 64-bit, Linux 64-bit. I don't produce one thing and run it everywhere. So what we want to do is take this idea, what we're calling variants, and make it pervasive. So a software component produces multiple different outputs, one for each platform. So this affects dependency management. So when I'm resolving my dependencies, if I'm building for Windows 32-bit, I need the 32-bit variant of my dependency. I can't be given the 64-bit variant. I can't be given the Linux binaries. It doesn't make any sense. It won't work. So dependency management's got to understand that. But it goes deeper than that as well. So it affects things like, if I've got a test suite, I need to run that test suite for every variant. I can't just run my tests for Windows 32-bit and go, well, it's probably going to work everywhere else. It doesn't work. Also affects lifecycle. So I want to be able to say to Gradle things like, Gradle, please build all my Windows binaries. Please build all my release binaries. Please build all my everything you can build here. So that's not quite enough. So another problem we have is that software in general produces multiple different types of artifacts. In Java, it's just the jar. That's okay. In the native space, again, it falls over. When I'm compiling against a C++ library, I need the header files. You can't give me the shared library. It just doesn't make any sense. When I'm linking, I need the stub files. When I'm running, I need the shared library. When I'm debugging, I need the debug files. So there's this idea that software is used in different ways, and based on how you're using it, you need different artifacts, and you need different dependencies as well. So again, we want to make this pervasive. This is just a general concept we want to bake into dependency management. So when you're resolving dependencies, you've got to know how you're intending to use the software. Am I compiling against this thing? So do I need the headers and the API dependencies? Am I linking against this thing? Am I running against this thing? And am I testing this thing? And so on. So we also want to more richly model the software that you're building. So at the moment we have conventions, and they work, but they're not very flexible. So what we want to do instead is be able to say, Gradle, I'm building a Java library. I'm building an Android application. I'm building a native executable. I'm building a web app. I'm building a my custom type of thing that runs on my custom type of container. So there's two things that lets us do. So basically that's a much more descriptive and high-level expression of what you're building rather than saying apply plugin Java. And that just fundamentally means that the automation can be more powerful. That's in two ways. We're not leaning on conventions so much. We're instead going, we want high-level descriptions of your software. You're not necessarily going to give up any convenience here. So it's not necessarily a bad thing, but it's a much richer thing. It's much more flexible. Because things don't have to make assumptions here. They don't have to rely on hard-coded convention names or configuration names or task names or directory names. Things can be more self-describing, and that makes the thing less rigid. It also means that plugins can collaborate in better ways. If we have models that plugins produce and models that plugins consume, the plugins that are consuming these models don't need to care about the details. They don't care how that plugin decided what the model was. They don't care how the things being described get built. They can just use them. So the goal here is it's all about flexibility. It's all about making Gradle richer and more flexible. Key thing here is also extensibility. So we want to tear down the distinction between models that Gradle provides and models that aren't core. Because we can provide models that describe Java libraries, but we can't provide models that describe everything and every possible thing that you want to build. So it has to be extensible. The third item here is the plugin ecosystem. So we've seen this in action already. The idea here is to make the ecosystem richer. And there's a few things we want to do here. So we want to make it easier to write plugins. So that's better tooling for testing, for publishing, and so on. We want to make it easier to share plugins within your organization and also with the community. So we've got that central repository, and we've got that plugin portal. That's for the community. So making it easier to find plugins. Again, the plugin portal, go there, search, there it is. And to use them as well. So that's things like the simplified DSL that you've seen. It's things like class loader isolation, so you can use different and interesting combinations of plugins in your build. So the final roadmap item is the developer experience. So, I mean, we've already discussed this a little bit with the scalability. If we make Gradle faster, the developer experience is better. There's other aspects here as well. So we want to make the tooling richer. So that means growing the tooling API to expose more stuff, make it extensibility of that better. Again, it's all about tearing down the distinctions between core and not core. We want to let the tooling API do new kinds of things. So an example of this is we're going to be able to say, through the tooling API, Gradle, can you run this test class? Can you run this test method for me? So Gradle spins up the right task, runs all the right dependencies, does all the right setup, does the teardown. If you're using some distributed test framework, the tests get sent off to the right place. So what this means is that you've got a single source of truth for how to build and test your software. The IDE and the command line are doing the same thing. The developer and the CI build are doing the same thing. Another thing we want to tackle is the comprehension and discoverability aspects of Gradle. So this again, this is another pain point, I think, particularly for people who are new to Gradle. It's like, what's going on? So we want to give better insight into what's going on. Where did this task come from? Where did this setting come from? Why is this task being run? Why didn't this task get run? Things like that. And then there's build authoring. So that's things like content completion in the IDE. So that's the roadmap. There's 4 things. There's make Gradle fast, make it powerful or more powerful, make the ecosystem richer, and make the experience more pleasant. So that's the plan. So scaling Gradle. So the first thing we want to look at is where's the problem? And there's a few, but the main one we want to tackle, at least initially, is model configuration. So this is the bit of the build early on where Gradle takes all the build scripts, all the plugins and user input and setting scripts and init scripts and Gradle.properties and whatever else, munges them all together, produces a model for all your projects, a bunch of tasks, and then a graph that it can actually go and do something useful with. So where's the issue here? Why is it slow? And there are two main reasons, or 2 main problems. So the first is that any piece of build logic can change anything. So I can have a script that reaches over here to this project and gets some stuff, and over to this project and gets some stuff, does some work, pushes something over there and change it over there, change something over in this project. So it's completely unstructured. And that logic can do it, that build logic can do these things pretty much at any time as well. So it can register some hooks, maybe after evaluate, maybe after a task gets executed, maybe after the projects are loaded, to do stuff. And Gradle has no insight into what's going on here. It has no idea what each piece of build logic is touching. So because build logic is reaching into certain things and touching other things, there's these implicit dependencies between all the bits of build logic. But Gradle has no idea what those are. So the net result is that Gradle basically has to configure everything, all your projects, all your tasks, from scratch every time you invoke the build. Because it doesn't know what the inputs are, doesn't know what the dependencies between things are, so it just has to go, there's everything. So this is bad, clearly. There's a few problems here. The first is that it's doing unnecessary work. So if I do Gradle clean, Gradle goes and configures all the tasks for building the project, for testing it, all the functional tests, for releasing it, for publishing it, for generating the ID files, just everything that you could possibly do with this project, Gradle configures it and then goes, I just need to do clean. And again, if I'm working on a large build, I'm working on some core library, doesn't have many dependencies, I do Gradle test, Gradle goes and configures every single project in the build, even though only that stuff is needed. So all these other projects don't need them. Unnecessary work. So Gradle also isn't able to reuse any of the work that it's done. So build logic generally is pretty stable. It doesn't change very often. Your software can be changing a lot, but generally the description of how to build that software doesn't change. So when you invoke Gradle and you say, please test this stuff, the model that it builds, or the models that it builds, they're almost always the same as they were last time you invoked Gradle. But because Gradle doesn't have any idea about the dependencies between things and the inputs of things, so what affects the model, it just has to start from scratch. So because Gradle doesn't, it gets better. Because Gradle doesn't know about the implicit dependencies between the bits of build logic, so it doesn't know who's touching what and when, it has to run everything in the same order every time. So that means, of course, you can't parallelize any of this stuff. And you can't distribute it either. There's also, it's not just about performance here as well. This lack of insight means that as a human, it's really hard to reason about what's going on once your build logic gets to a certain size. And that size isn't very big. If you've got some core plugins and you've got some community plugins and some enterprise plugins and a build script injecting some stuff and a couple of init scripts over here, there's just stuff coming from everywhere. It's just, I don't know what's going on, so I kind of get it working, and then it's working for a while, and something changes, things break in strange ways, dependencies are missing, some properties gone missing. So it's not just about the performance, but it's also about the comprehensibility. So there is a core piece of Gradle that doesn't have these problems, where we do actually successfully scale, and that's the task graph. So these blue things, the blue squares are the things, so the jars and the source files, and the white squares are the tasks that are acting on them. So I've got some application, it depends on some core library, some UI library. Cool. When I go Gradle, please build my core library. It runs this task to compile the source into the library, and that's all it does. All this other stuff, don't need it, it doesn't touch it. So it's not doing unnecessary work. Because Gradle knows the inputs to this stuff, it can do up-to-date checks. So if you do Gradle, please build this core jar, and it's already built it, and the source is up to date, it skips that task. So it's reusing work it's already done. This graph is parallelizable as well. So I can be building my core jar and my UI jar at the same time. No worries. It's actually also a much simpler model when it comes to ordering as well. You just have to get one basic concept. Gradle doesn't run a task until all its inputs are available. That's all you need to know. Then it's easy. When does this run? Well, when they're ready. That's it.
There's an implication here that source are files. I kind of think that source should include command line properties.
Absolutely, absolutely. This is just a simplification. But the idea is that there's inputs, and generally that's right. So if I'm compiling Java, I have. Sorry. The question is, well, it's really source isn't the only type of input here. There are other types of inputs. So if I'm compiling Java, I've got source files, I've got the command line, the compile options, and I've got the version of the compiler that I'm compiling as well. It's another input, an implicit input, still important. So yes, definitely, absolutely. So this is all good. This can scale nicely. We can distribute this work. Nice, simple ordering characteristics. Nice and doesn't do unnecessary work. Reuses work. So let's reuse this approach for configuration. So if you think about what a task is, it's just a function, takes some inputs, produces some outputs. Think about what build logic is. It's the same thing. Takes some inputs, does something with them, produces some outputs. And the difference is really only the types of things that those functions are acting on. Tasks generally work with source files, they produce files, but they also take models as inputs, the compile options, for example. Configuration actions generally take models as inputs, they take user input as input, and they produce other models, and they produce tasks. So what we want to be able to do is come up with some way to take that giant monolithic configuration phase and bust it up into smaller pieces with inputs and outputs. And from that, we can figure out a graph of dependencies and do things in the right order. So how might that look? So here's an example. So again, this is a simplification, just to illustrate the idea. I would expect what we want to end up with is a much finer grained graph than this. And of course, there's many more inputs here, but this will just give you the idea. So what we have here, we have our application again. So there's some model for the application. There's some description of how to build it. Where are the source directories? What are its dependencies? What's the platforms it targets, and so on. So that model is produced by this piece of logic here, and its input is the application.gradle. So in order to figure out the application model, I need to run this piece of logic, which will run the Gradle app.gradle to produce the model. Same with the core library here. It's the output of this piece of build logic that runs the core.gradle to configure that model. So a few more examples here. So in order to build my application model, I need to know what the compile class path is. So that's a thing, that's a model. That's something we need to know before we can start building. So in order to do that, I need to invoke this piece of logic to resolve the dependency graph. So its inputs are the application model. It takes the application model. What are the dependencies declared in there? Let's start resolving them. It has a dependency on the core library. So I'm going to need its model as well. It's an input into this dependency resolve logic. Does its thing, out comes a class path. Another example over here, I have some test suites for my application. So I have a piece of logic here that figures out what those are. It uses the application model to do so. So the application test suite model might be things like, which version of JUnit do we want to test with? Which platforms are we testing for? Where's the test source? And so on. So now if I go Gradle, please build this thing, It goes, okay, I need the compile class path for this guy. So I need to invoke this logic. So that means I need the application model. So to get the application model, I need to run the app.gradle build script. Does some resolving. I need the core library model. Okay, in order to build that, I need to run core.gradle. But it doesn't need to do this stuff, because I haven't asked it to do any tests, so I can just skip that. So this could be quite expensive. So an example of that is in Gradle's own build, we define a test suite for each, a compatibility test suite for each previous released version of Gradle. It tests current Gradle against a particular release. In order to do that, we go and hit services.gradle.org to figure out what all the releases are. So we don't want to do that on every invocation of Gradle. So we have workarounds in our build script to try and cache that stuff. We try and guess whether it's changed. We try and guess whether we need it or not. With this approach, we can just get rid of all that stuff. We can just go, we run that once a day. So if that takes 500 milliseconds once a day, we don't care. So we can really simplify that logic. So an implication of this approach is that for logic that doesn't get executed very often, you can just write nice, simple logic. You don't need to worry about the fact that at the moment, it's a hotspot. Every time you invoke Gradle, it's being called. Now, it's not. So nice and simple. So Gradle's not doing unnecessary work here. And now, because we know the inputs to these things, we can do up-to-date checks. So if I say, Gradle, please build my core library, it goes, oh, I've already configured that model in the past. I'll load it up. Core.gradle is the only input to it. In this example, in general, that's not true. Core.gradle hasn't changed. I can reuse the model. And so I can do that transitively. So I'm trying to build this guy. That hasn't changed. That hasn't changed. It means I don't need to resolve again. I can just reuse that from last time. So we want to be able to take these models and persist them so we can reuse them across invocations of Gradle. But what we can also do in the daemon is hang on to those in memory so that when you go, Gradle, please build some stuff, the model's already there. It's already loaded up. It's ready to go. We can do our up-to-date checks. Up to date, good. So this is also parallelizable. We can be configuring the core library model while we're configuring the application model. So even though there's a dependency between the software, there isn't a dependency between the configuration of how to build that software. So we can be doing that work in parallel. We can be doing this work in parallel as well. We can be calculating the class path while we're figuring out what the test suite should be. And it's distributable. If we can take Gradle, app.gradle, move it over there to another machine, we can do the work over there and bring the result back. So we've got a nice, simple abstraction, and we can get some really interesting things out of that. So now that Gradle knows the inputs to a particular model, the daemon can start watching for changes to that model, those inputs. And it can start rebuilding those models in the background. It knows what you've been working on, so it knows what it can anticipate what you're going to need. It can certainly predict that. Watch for changes, load it up. So I edited a build script. I go over here and say, Gradle, do some stuff. It's already built the model for me. It's ready to start building stuff. So this has a nice, this means nicer IDE integration. Firstly, we're doing smaller chunks of work. So each time you invoke Gradle, it does less stuff, but it's doing it in advance. So it's anticipating what you want to do. And we can also communicate that stuff back through to the IDE. Something's changed. Oh, the model's changed. The dependency graph's changed. Oh, I better tell the IDE about that. Another implication of this stuff is we have much more insight into what's going on, so we can tell you about it. So instead of one big monolithic blob of stuff, now we have smaller pieces. So we can do the same sorts of things we do with tasks. So we can draw a graph and say, hey, here's all your configuration logic. Here's how it all hangs together. Here's who's doing what, to what. We can do logging. We can do a profile report, and so on. So what's this actually going to look like? There's two pieces here. So first is we'll add a new DSL that you use in build script, in the build scripts for defining your build logic. And there'll be a Java API that your plugins can use for defining your build logic. There'll probably be some Groovy sugar on top of that as well, make that nice and easy to use from Groovy. The DSL will sit alongside the old DSL. So there's a mock-up here, and it's scoped in this block, so it's separate, but you'll be able to use it alongside the old stuff. Be backwards compatible. There's some bridging between the two worlds, so the new and old world. The old stuff will be there for a long time, so it'll be a long migration path there before we deprecate it eventually. Similarly with the Java API, you'll be able to do old style build logic, new style build logic, mix them in the same build. The old stuff will work for a long time. We'll eventually deprecate it. So here's a mock-up of what the DSL might look like. This is just a mock-up, so this isn't final in any way. It's just to give you an idea of what it might look like. If you've been using the native plugins, you will have seen some of this in action already. So we have started down this path already. There is code that provides this DSL. So there's two pieces of build logic here, two build rules, or model rules. The first one here is a block of code that configures a library called mylib. And the second one here is a block of code that defines and configures a task, some task type, custom type. So if something in the build says, Gradle, I need the mylib library model, Gradle goes, okay, cool. I run this block of code. If nothing asks for that in the build, Gradle doesn't run that piece of code. Doesn't need to. Similarly, if something asks for the sum task, or it asks for all the tasks with type custom type, or it asks for all the tasks, Gradle goes, I know about that. I define the task, I instantiate it, I run that code to configure it. And again, if nothing asks for that, Gradle doesn't do the work. Now, inputs and outputs are generally inferable here. So the output Gradle can figure out by the context. You've already said what the output is. This configures that. So this piece of code configures that library model, so that's the output of it. This piece of code defines and configures this task, so that's its output. And this giant path here is an input. Gradle can, with the Groovy, Gradle can inspect the Groovy AST and statically figure out that's a reference to some model. It's a reference to the mylib model. So that means it's an input to this piece of build logic. So if Gradle needs to run this, it knows that it first needs to get the model for the mylib library, which means it needs to run that. We might do something to make this a bit more convenient, but that's just to give you an idea. So not very exciting when there's two build rules in a single build script, but if you start having this over in some core plugin, having another convention plugin over here that changes the conventions, a root build script that's injecting some stuff, it gets a bit more interesting.
What are the assumptions behind this? Like when we saw the plugins for the new plugin architecture, there was some pretty restrictive assumptions so that it could be inferred against.
Yes.
Are there similar kinds of constraints here? Because I could see if you could dynamically generate stuff, you're sort of back in the, I have to run everything in order to.
So the question was, what are the restrictions on here that Gradle, that let Gradle do this stuff without needing to run everything every time? That's still a bit of an open question. They won't be as restrictive as the plugin stuff. So, and the goal isn't necessarily there's a trade-off here, right? If this task is only run once every 2 years, it doesn't matter whether it's dynamic or not. So it's not an absolute thing here. We don't necessarily want to prevent every possible piece of unnecessary work. It's just whether it's worthwhile for the build author to do that. So there'll be a degree of opt-in, I think. If you follow this rule, you get this behavior. If you don't want to follow that rule or you can't follow that rule, you give something up. And the exact details we're still sort of working on. Definitely not as restrictive as the plugins block. The reason for the plugins block being so tightly tied down is that it's just so fundamental to what the model is. So we really want that to be fast. That's involved in every invocation of Gradle. It just has to be. So it has to be really fast. This stuff, a trade-off. And I think things like the giving you insight, so the profiling report can let you make that decision as well. What's going on with this build? Oh, my build, that we'll be able to say, that piece of build logic took this amount of time. That piece of build logic took this amount of time. And go, now I know where to focus my energies. That needs to be, I need to follow some rules for that. I get faster, that stuff, I don't care. All right.
You're going to cache the input output of all the big data?
Yeah, so the question is, are we going to cache all the inputs and outputs? The models, yes. So the types of inputs that we understand will cache. Inputs, so actually that's something else. So there'll be some way to declare inputs and outputs that aren't models. So some pieces of build logic use files as inputs. They use user input as input. So you need to be able to declare that stuff. The stuff that Gradle understands and that it can cache, it will do so. The stuff that it can't, like the user input, it just has to deal with that. So that kind of brings us nicely to caching everything. So we have this graph of functions. Functions take inputs, they produce outputs. Most tasks and most configuration actions, but not all, are deterministic. So if you've got a given set of inputs, it will always produce the same set of outputs. Which means you can cache that result and reuse it later. So our plan is to start with using this caching in the same, within one build. So this gets interesting already when you're getting into building multiple variants of something. So say I'm building an Android application, I've got a debug variant and a release variant. In general, those two things can have different resources, but often they don't. So you've got a task over here crunching the resources for your debug variant, and a task over here crunching the resources for your release variant. And they just, in your case, happen to have the same set of sources inputs, the same set of configuration, the same version of Android SDK. So what Gradle can do is go, I've already run the debug stuff and it produced these resources over here. Now you want me to run that. It's got exactly the same inputs. So I can just take those outputs, copy them across. Don't need to run the work. So if we've got a deterministic function and we've captured all the inputs, we can do this caching. So first within a build, then we can move to sharing it across builds on the same machine. So if I'm a developer and I've checked out the same stuff a few times, maybe I'm working on a couple of different branches. If I've compiled this Java source with this settings and this version of the Java compiler, I can just copy those class files over here. I don't need to compile over here. It's also useful for CI builds that are running lots of builds in parallel, potentially on the same machine. If this branch over here, I've built these source files with these settings, this version of the compiler, and I'm running this build over here with the same inputs, I can just copy that across. And then the ultimate goal is to do this globally, so have a single shared cache across a bunch of machines, across the whole organization. So what that means is if anyone or any machine has compiled this source with these inputs and this version of Java, I can just go over there, grab those class files, and bring them down. And we can do this for any of these functions, so it's not just about build outputs. It's also about models. So if my CI build's configured all 4,000 projects that I'm just about to build, I can just go and grab that model, bring it down, and I'm ready to build stuff. Then we can get the daemon involved here. So the daemon knows what you're working on. So I go, the CI build's just configured all that stuff. You're going to need that in a moment. I'll go and get it, grab it. And particularly common tasks, they're just containers of smaller pieces of work. So an example is test execution. So you've got the test task. It's really just a container for running that test, and that test, and that test, and that test. They're all independent pieces. Generally, not always, but generally. So what we can do is we can take that node in the graph, that test task, we can take it out and we can replace it with a node for each of the tests. And then just feed that into the mix so that then each test can be run in parallel, they can be taken and run distributed. So mixed in there with all the other work that Gradle needs to do. And can be running some tests from here, run some tests from there, mix it all up. So another example is source compilation, particularly in C++ and the native languages. We basically just compile each source file one at a time. They're all independent. So what we can do is take that C++ compilation task node out of the graph, swap in a node for each of the source files, just let it into the mix. Then Gradle can do the up-to-date checks, the incremental build on each source file independently. So if you've got this global cache going on, if someone has compiled this source file with these header files, these compiler settings, this version of GCC, I can go and get that object file, bring it down. There might be other source files that have changed. I still need to build them. Some have been removed. I need to clean them up. But the ones that haven't changed, I can just go and get them. And then, of course, we can do that in parallel, and we can distribute that. So what we're ending up with here is a single unified graph of work that Gradle does. Each piece of work has some inputs. Each piece of work has some outputs. From that, Gradle can figure out what order to run them in. It can figure out whether they're required or not. It can figure out whether it's already done that work. It can go and fetch that work. So this is our plan for scalability. Single unified graph of work. From that simple abstraction, we get really nice performance characteristics. We get insight. We get comprehensibility. We get lots of nice benefits. So I'm going to leave it there. So this is interesting stuff. If you want to get involved, there's a few ways you can do so. You can try it out and give us feedback. So we're going to be developing this stuff incrementally. It'll be incubating for a while. We'll stabilize it over time. Some stuff's already there. So play with it. See what you like, what you don't like, what makes sense, what doesn't, what's broken. Let us know. Use cases are always really, really useful as well. Tell us what you're trying to do, why you're trying to do it. Helps us form the model. You can send us code. That's always welcome. So a way that organizations can help out here is through the open source partnerships with Gradleware, where you essentially sponsor some of this work. So an organization can get some pain relief and contribute back to the community as well. And then we're hiring as well, so you can come and join us and work on it. We're looking for R&D engineers to help us with this stuff. So I'm going to leave it there. So are there any questions? Yes.
Are there any guidelines you give?
So the question is, do we have any guidelines for how to start using this stuff as it becomes available?
Or structuring our build scripts in a way that will make it easier to adopt, say, the model?
So how do we structure our build scripts to make it easier to adopt this model? I think there's a few aspects to that. I think so plugins are an important part here, I think. So getting those responsibilities in one place rather than kind of smeared across a bunch of build scripts is probably a good approach. So it's really what's the responsibility? Who is responsible for stating this piece of logic is an important thing there. Is it something that is an organization-wide thing that someone from that some plugin produced by the organization should be stating? Is this something specific to this project that should be stated in a root project? Good conventions that match what you're doing, I think, is another thing. So you have to state less. So build scripts are about stating the exceptions generally to the conventions. So the better the conventions that you're using match what you're actually doing, the smaller your build logic in build scripts. So it's just general stuff, really. I don't think there's anything specific. Yeah, that's a good one. Yeah. So, and this has always been the case, right? This isn't specific for this stuff, and for 2.0 is don't have projects reaching across and touching other projects. It was never a good idea, and it's a shame we put it in there, and it's going to go. So and again, it's about responsibilities. If this guy over here is a sibling of this guy and he's reaching across and doing stuff, there's some wrong partitioning of the responsibilities there.
Do I not care? You know?
Yes. So the question is, how do you deal with, or how do we intend to deal with, build outputs where there's environmental stuff getting jammed in that's sometimes relevant and sometimes not? I think what we'll have to be able to do is give you a way to express whether you care or not about that. So if I've got timestamps in my development build that I'm testing locally that aren't right, I don't care. I don't care at all. So I should be able to say, for my debug variants, timestamps don't make it. I don't care. Just if what I'm interested in is well, you want to be able to say, for the purposes of development, compilation of C++ code is deterministic. So pretend there's no timestamps there. For your release builds, you might do something differently. You might say, actually, they are relevant. And so the tool chains can say, well, Visual C++, that puts timestamps in the object files. So I can't reuse something from another machine. I actually need to build it here. And I have to build it now because the timestamp's involved. So it's about being able to express that stuff and say when it matters and when it doesn't matter. And it's also about being able to provide better ways of describing these outputs as well. So that you can say, this isn't just a file that's the output. This is a native runtime object file. And so that has certain implications here. So we can say, well, okay, there might be timestamps in it. So sometimes the hashes are going to be different, but if it's had the same source, same compiler setting, same compiler, it's the same. So, yes?
Rather than copying artifacts from the build system onto the client machine, why not go the other way and send the source over to the build system?
So the question is, why copy the outputs from the build machine, from the local machine? Why not copy the source? It's essentially, why are you doing the work locally? Why aren't you doing the work remotely? Yes, absolutely. That's exactly what we want to be able to do. Yes. So implicit in all this, I don't think I made it entirely clear, was that we also want to be able to distribute the work. So if there's a graph of work to do, and when you need to be able, once Gradle's figure out what it needs to do, you need to be able to take that work and send it to places. And you need to be able to distribute it across a bunch of machines. First to scale it, but also sometimes you need to do that because that's where the tools are. If I'm building for Windows, I need to get that work onto a Windows machine. If I'm building for Spark, I need to get that onto a Spark machine. So it's not just about scale, it's also about sometimes I need to do that. I might have a source generation tool with a node lock license, and everyone's got to bank up sending their source there and getting it generated and bringing it back, and then I can distribute it. So yes, we definitely want to be able to move the work around as well as the artifacts. Yes. So, Jay. So the question is, when can you inject new behavior into the build? These are still open questions to some degree, exactly how much we want to make that, to lock that down or not. We do want so the idea is that behavior is always added by, not always. There's two things that provide behavior. There's plugins and there's build scripts. So everything that isn't a build script is a plugin. That's the abstraction. And then where do these plugins come from? Well, we want to have a bunch of different places where they could come from. But what we do want is we want to make explicit those dependencies on those plugins. So rather than have this implicit build source thing that's available, that's kind of inherently available to everything, we want to give you ways to explicitly declare that. It might be saying explicitly in a settings.gradle saying all projects depend on the build source project. That's fine. There will be conveniences for doing this across a large number of things, but it's still an explicit statement. And so I think we want to head in that kind of direction. Is we want to know up front where your build logic is, where it's coming from, who's contributing it. But there's no reason why we couldn't say, well, build source is just. We could do this. We might not. I don't think we want to, but we could just say, well, build source is just an implicit dependency of everything. So if it changes, everything's changed. And that's the choice. That's the trade-off you're getting for the convenience of build source versus the performance of having to. If that changes, it has an impact on everything. So there's still a few decisions we need to make exactly how that's all going to work. Generally, we shouldn't be losing any use cases. So if there's a use case you can solve now, you should continue to be able to solve it into the future. You might have to restructure things a little bit over time, but generally there's no use cases we want to drop.
About changing the build scripts, when you're going to change the graph of the configuration element, you're going to have some kind of delta from what is cached already, or you're going to...
So the question is, when the build script changes, are we going to do a delta with what's there? What we're going to do is bust up that giant project model into smaller pieces and just rebuild and track the dependencies between the different pieces. So the pieces would be things like the dependencies for a library, the test suites for a library, the source sets for a library, so that if something changes, we'll probably still rebuild it in its entirety, but what we won't be doing is doing that at the project level, we'll be doing that at a finer grained level. So if something that affects the dependencies change, then we can just we throw away the dependencies and recalculate them. So that's the idea. We'll see how that pans out. But even just doing this at the project level rather than the universe level, that's already a big win. So if that's as far as we get, still a much better state than we're in now.
So you're going to have a way to say that the output of my change is messing up the graph. If you start to mess up other.
Well, so the question is whether we'll have a way to say my change impacts these things. What we want to do is say, I have this as input and this as output, and then Gradle can figure out that bit for you. So that's all just transitive stuff. If this guy has this input and that input changes, then implicitly everything that uses its output as input is also affected. But Gradle can figure that stuff out. We don't want to have to get you to tell us all that stuff. So
this kind of presumes that all tasks are pure functions.
yes.
That pretty much includes tasks that may shell out and call scripts that they haven't declared as explicit input.
Yes.
Will you prevent that from happening so that?
So the question is, essentially, how are we going to prevent things that aren't deterministic from being used? And the answer is no. So this needs to be, you might need to opt into that. By default, Gradle might say, hey, and we're certainly going to assume that this thing is deterministic. So if you say this has inputs and this has outputs, we're going to go, okay, cool, that means you're deterministic unless you tell us otherwise. But you should have a way to say this isn't deterministic. You need to run it every time. Those things tend to be at the start of, like deep down in the graph, or right at the edge of the graph. So they're either first in the build or last in the build. So what we can do is run them, snapshot what they produced, and then everything else can be incremental from there. And same at the other end, right? We're incremental. Now we have to run this thing. But we're short-circuiting as soon as we've noticed that something hasn't changed, that we do know about, we can short-circuit it and stop the work propagating. So if something deep in the graph isn't deterministic, we run it. It actually, even though it's not deterministic, it produced the same thing as last time, so we can stop there. But we do need to be able to deal with these things. There's definitely and absolutely things that aren't deterministic. So tests is a perfect example of that. In general, tests aren't deterministic. That's just how it works. So we want to be able to go, these are tests, they're not deterministic. Okay, let's just run them every time. So we do need to tackle that. Exactly how that's going to work in the DSL, still an open question. But, so we'll have to leave it there. Thank you, everyone.